Okay, in this podcast I'm going to do a review of kinetics. I'm going to do a lot of problems along the way, so my recommendation is when I get to a problem that you pause and see if you can do it yourself, and by trying that, and if you don't get the right answer, then you can pay attention to what I do, and it'll click a little better. Okay. So, first thing we have to talk about when we talk about kinetics is what has to happen for a reaction to occur. So if I think about, I have two things that have to collide. There are effective collisions, which will occur at the right spot on a molecule to make it break the bonds. And then there's ineffective collisions that hit at the wrong spot and don't result in breaking a bond. So one of the requirements of a collision is that it must have a collision with the proper orientation to break the bonds. So I need proper orientation of the collision. And the second piece is it has to have sufficient energy. So I can't just like glance to particles colliding. They have to smack each other. So this is one way to think about having sufficient energy. All reactions have some amount of activation energy, some amount of energy that needs to be overcome in order for that reaction to start, and that's the energy of the collision. So some reactions, if I look over here on the right, the activation energy is very high, and there are a relatively small number of molecules that will have sufficient energy to break those bonds. So you know kinetic energy is measured by temperature in Kelvin. So this is of course temperature dependent. And at the same temperature you might have a different reaction where the activation energy is very, very low, and at some given temperature most of the molecules or particles have enough energy to break those bonds. So it depends on the reaction that you're doing and the temperature that you're at. So if I have a certain distribution of particles. So this is a Maxwell-Boltzmann distribution. We've seen this before. The x-axis here is kinetic energy, and this is a fraction of molecules. So if I have a certain temperature, then I'm going to have some distribution of kinetic energy amongst those molecules. If I raise the temperature, my average kinetic energy is going to be higher. Remember that the distribution of the particles changes, it broadens, okay? The area under both curves is exactly the same because they all represent a total of 100% of the molecules. But what happens when I have a higher temperature is I now have, originally I had this portion of the molecules that had sufficient energy to overcome the activation energy barrier. Now I have a much larger distribution. Nice messy there. So the words you have to use on the AP exam is you have more particles have sufficient energy to overcome activation energy. Now a lot of students will say write on the FRQ and not get the point because they wrote that at a higher temperature the particles are moving faster and therefore they'll hit each other harder. That's not going to get you the point. You have to say what's happening here is at a higher temperature more particles now have sufficient energy to overcome the activation energy. Okay, so if we think about a reaction and we were to plot, let's see here, we have the reactants. We start with some amount of reactants. Whoops. And initially we have no product. Over time, we can show what's happening to the concentration of reactants and what's happening to the concentration of products. So the question is the rate going to be constant? And the answer is generally it's not going to be constant, because what happens here, you know, when I have a high concentration of reactants, okay, then I'm going to have a more likely we are more likely to have a collision because they're closer together and they're going to be easier to hit one with the right orientation. As I proceed in the reaction, the concentration of the reactants goes down, and as a result I have fewer collisions. So the same thing's happening with the products. You sort of really see in the inverse here. As the reactants get consumed, the products get made faster initially. When I have a lot of reactants, a lot of bonds being broken, I can form new products. Okay. If I were to plot the concentration versus time, I could determine my average rate by looking at the total change. It's the change in concentration of my reactant over the change in time, right? If I wanted to know what the rate was at any given point along that graph, then I can find the slope of that tangent line. Okay, so remember what a rate law looks like. So if I have a balanced equation where I have A plus B becoming C plus D, and they have the corresponding coefficients, then my rate law is rate is equal to K, which is the rate constant, times my concentration of my first reactant raised to some power X in my second reactant raised to some power Y. A couple of really important things to notice here is the rate law only has reactants. It does not have products like equilibrium expressions do. And that these x's and y's, these exponents, they do not come from the coefficients of the balanced equation, which is why we call them x and y and not a and b. Okay, so let's say I had this reaction, 2NO plus H2, and it gives me those products. Let's say the rate law was determined to be rate equals K times NO squared times H2. Now it's important to recognize, like we just said, that these exponents do not come from the balanced equation. Now in fact I do have a 2 here and a 2 here, but that's just coincidence, right? I also have a 2 H2 and I only have a 1 here, an implied 1. So if we're talking about this reaction, we would say that it's second order in NO, that's the exponent. It's first order in H2, and if I add those together, I get third order overall. Orders can be 0, and they're 0 when it doesn't matter what my concentration is, the rate doesn't change. And orders can also be fractions. Okay, so let's take a look at what a rate law tells us. So here we have this rate law, and let's look at what it tells us. What happens to the rate if H2 is going to be doubled while NO remains constant? So let's say I start with a concentration of 1 molar squared, right, for the NO, and the H2, let's say, is 1 to start with, and then I double NO, H stays constant. I've gone from this equals 1, this equals 4, so I have quadrupled my rate. Okay, if I double what's in the brackets and then I square it, so I'm quadrupling my rate. Okay, so let's take a look here. We want to determine the rate law and rate constant for the following reaction at 450 K using the data in the table. Here's where I suggest you go ahead and see if you can solve this yourself. See what you remember. Okay, so what you want to do is you want to first look at where I keep one reactant constant. Here I'm keeping X at 0.01, and I'm changing Y, and I am tripling it, right? And here I got to look at what happens to the initial rate as a result. I am increasing it by also a factor of 3. Okay, so if I double this and this doubles, or I triple this and this triples, then the rate order is 1. Okay, now I want to look at what happens with the other reactant. So here I want to keep my Y constant. I'll keep it at 0.03. I'm doubling my X, okay, and my what happens to my rate is it goes from 0.48 to 0.192. If I put 0.192 over 0.048, I get 4. So if the concentration is doubling, the question is 2 to the x is equal to 4. What is x? Okay, this is what's happening to my concentration. This is what's happening to my rate. Got to figure out what x is, right? So if I'm doubling my concentration and my rate changes by a factor of 4, x must equal 2, and this is going to be x squared. Okay, so we can write integrated rate laws that help us determine what concentration we have at any point during the reaction. All right. So we were looking earlier at what happens in a typical reaction as the concentration of the reactant, this is always going to be concentration of reactant, goes down, that the over time it's going to get consumed faster in the beginning and then more slowly as I have less reactant molecules to collide. If I take that what's happening there and I plot the log of A, this is just for a first order. If I plot the log of the concentration of A versus time, I get a straight line. And the slope of that line tells me what K is. Now remember, K is always positive. It's always a positive number. So if I have a negative slope on one of these graphs, the slope is going to be the negative of K. Don't forget that. A lot of students will get that wrong on the test. Okay, if I look at the equation sheet, it gives me this equation, the natural log of the concentration of A minus the initial concentration of A, which would be where I start, is equal to negative KT. Okay, I think it's often easier to think about that equation this way, but whatever works for you mathematically, as long as you get the right answers. Now, if I'm dealing with gases and I'm not looking at concentrations, but I'm given pressures, the same thing applies. I can plot the natural log of pressure for a first order reaction versus time, and I also should get a straight line. So I can plot either molarity or pressure. Okay, so let's say I was given this data and I wanted to see what the order for the reaction is. The first thing I could do is, if I were to take this data and I take the natural log of these values and plot them versus time, and I get a straight line, then I have a first order reaction. That's a test for first order. Okay, so let's take a look at a problem. So I have a rate constant of a certain order is given to me, and the reaction starts with a concentration of 0.25. You want to know the concentration after 1.5 minutes. So go ahead and see if you can figure this out. Okay. Alright, so I'm going to, this is a first order reaction, so I'm going to use my integrated rate law, and I like this version. It should be A0, and these are concentrations, right? Is equal to minus KT. Okay. So this is the natural log of concentration of AT. I'm given that this is, the initial concentration is 0.250 molar. That's equal to the negative of my rate constant, which is 5.24 times 10 to the minus 3, and that's over seconds, and I have 60 seconds is 1 minute, and this is 1.5 minutes. Okay. So if I put both of these things to the power of e to the log of the AT is going to give me AT over 0.25 molar equals e to the to all of this multiplied together is going to be, and all of this together, by the way, is negative 0.472. So if I do e to the minus 0.472, I get 0.624. So AT then is going to be 0.624 times 0.25, or 0.156 molar. I'm going with 3 sig figs here. 3 sig figs. Rate laws and rate constants are experimentally determined, so they do limit your sig figs. Any constant that is determined experimentally is a constant where the sig figs do limit what your answer sig figs can be. Okay, so we can use integrated rate law to determine half-life. So the half-life of something is determined as the time required for the concentration of a reactant to decrease to half of its initial. Okay, so at time 1/2, my concentration is half of what I started with. This is what I started with. And here's what it looks like. So if I have, let's say, I don't know what there is, if I have 20, if I have 16 particles to start, my half-life is the length of time it takes for me to get down to 8 particles, or 8 moles. And what you'll notice here, and this only happens with first order, is the time it takes for each half-life for the concentration to be cut in half is the same. The length of the half-life is constant. It doesn't change as time goes by. So the what I see here is the first half-life is 1 minute. Let's say it's minutes. The second half-life is 1 minute, 1 minute, 1 minute. And that's actually a good indication, if you see this happening, that you're every time interval, every half-life, you're going down by half of the concentration, then you know you have a first order reaction. All right, so let's take a look at this. This is an actual question that was on an AP test. So the graph shows the results of a study of reaction X with a large excess of Y to yield Z. The concentrations of X and Y were measured over a period of time according to the results. Which of the following can be concluded about the rate law for the reaction under the conditions studied? Okay, so we see Y isn't, the change in Y isn't changing. Okay, so we can't say Y is a first order, so that's not an option. But let's take a look at what's happening with X. If I start with 0.2 molar here, if I get down to exactly half that amount, it takes 1 hour. That's not quite a straight line, but it takes 1 hour. To get down to half of that value takes me 1 more hour. And the fact that reducing the concentration by a half always takes the same amount of time tells me this is first order. So what I know is this reaction is first order in X. And that's the answer to that question. Okay, now you can derive this, but we're just going to cut to the chase. And this is a shortcut only for first order. Okay? And what this equation tells us, the half-life, the time it takes to get to half of the concentration, is 0.693 over K. This is on your equation sheet. It is extremely helpful. You can get answers to half-life or K values if you know you have a first order reaction very quickly by using this equation rather than the full integrated rate law. And one of the things that's really interesting here is that the concentration is not part of this equation. So the half-life does not matter, does not change with the concentration. Okay. All right, so let's take a look at some half-life problems. So the first one says, I have a first order reaction. I started at 8 molar. Okay? And the half-life is 1 minute. What concentration would remain after 3 minutes? So after 1 minute, I'm going to have 4 molar. And I just think this is a lot easier than using integrated rate law. After my second minute, I'm going to have 2 molar. So I've got 2 half-lives so far. 1 more minute, I'm down half again. I'm down to 1. So I have 1, 2, 3 half-lives. My answer is 1 molar. Okay, so here we are. We're looking at, we are 75, first order reaction, given the rate constant, and the time required for the reaction to be 75% complete. Okay, so let's think about that. Think about what you would do here. Well, if I'm 75% complete, if I were 50% complete, I'd have half of my concentration left. If I were 75% complete, I'd have a quarter left. So if I started here, so what I have here is 1 half-life and a second half-life. So I have 2 half-lives, okay? So what I need to do is figure out what my half-life is, and then I'm going to double it, okay? So here I can use time at 1/2 equal 0.693 over K. All right, I'm given 0.693, I'm given K. K is 3 times 10 to the minus 3 seconds to the minus 1, and what I get here when I do this is I get 231 seconds, and because it takes 2 half-lives I have to double this, so it's going to be 462 seconds. So the next question here says, what if it takes 30% to be complete? Same rate constant. Okay, so let's think about what that means. If I'm 30% complete, I always have to know what I have left. So I'm going to have 70% left, right? So 70% of what I started with will be left. So if I use my integrated rate law, these are concentrations, right? Equals minus KT. Now what I could say is, this the natural log of, so if I started with 1 of these, then I have 0.7 of this left. So I have, this ratio is 0.7, right? The ratio of my concentration at my half-life is equal to minus KT. I know what the natural log of 0.7 is. It's minus 0.3566. And if I put that over my K, which is minus 3 times 10 to the minus 3, I get a time of 119 seconds. All right. The half-life for the first order conversion of cyclopropane is 17 minutes. What is the rate constant? Okay, so here's another easy problem. If you remember that half-life is 0.693 over K. This is a lowercase k, right? So if I want to know what K is, it's going to be 0.693 over my time at 1/2, okay? And I want units of s to the minus 1 for my K, so it's 0.693 over 17 minutes times 1 minute under 60 seconds, right? And what I get when I do all that is I get, let me see, I get 6.8 times 10 to the minus 4 seconds to the minus 1. There's no unit here, and minutes cancel out here, so I end up with 1 over seconds. Remember on kinetics how important units of K are, okay? You got to really pay attention to that. Okay, if you're doing really well, then this should be an easy one for you. Why don't you go ahead and try it on your own? Okay. So we're given the half-life. We want to determine the amount of time required to convert 30% of it to propene. Okay. Okay, so the last, I was going to say this looks like the last problem, but the last problem we were looking at what is the half-life. Now we're going to look at what is, the last one we're looking at what is the rate constant. Now we're looking at what is the time. Okay, so what I know is the natural log of the concentration over A0 is equal to minus KT. So the log of, if I've converted 30%, then I have 0.7 left. If I started with 1, I'm at 0.7 of that. That's equal to minus KT. Minus KT. So T is going to be the log of 0.7 over the rate constant, which I had in the last problem, which is minus 6.8 times 10 to the minus 4. This is going to give me an answer of 524 seconds, because this is seconds to the minus 1. So I have 1 over seconds, which gives me seconds. Want the answer in units, so I'm going to divide by 60 seconds in 1 minute, and I get 8.7 minutes. Alright, I want to do this one because you're going to see how easy it is if you think about it. First order reaction takes 456 seconds to reduce the amount of reactant to 1/16 of its original concentration. What is the half-life of the reaction at this temperature? Okay, so for any reaction, my first half-life gets me down to half. Then I get down to a quarter. Then I get down to an eighth. Then I get down to a 16th. So I have 1, 2, 3. Oh, I forgot this one. I started with 1. 1, 2, 3, 4 half-lives. So if I have a total time of 456 seconds and I have 4 half-lives, each half-life is going to be 114 seconds. Okay, so if I wanted to figure out what the order of this reaction is, what I want to do is I want to create a plot. As it turns out, there's 3 plots I can make. I can do concentration of my reactant versus time. And if I get a straight line, it is 0th order, right? If I plot natural log versus time and I get a straight line, this doesn't look quite straight, but if it was a straight line, I would be first order. And if I plot the natural log, I'm sorry, the inverse, or 1 over the concentration, I get a straight line, which that is not, then this would be second order. Okay? So here are the 3 plots. Anytime I'm given the data, I could do this. Now, I have never seen this on the AP exam where you had to determine, you had to do the plotting. What I have always seen is they give you the graph, and they say based on the graphs, what's the order? So if concentration versus time is straight line, remember K rate constant is always positive. It's always positive. So if this has a negative slope, K is always going to be the slope of one of these lines, the slope or the negative of the slope. So if my slope is negative, then my K is the negative of the slope, right? Same thing with the natural log versus time. This is a first order reaction. It's the tell for first order. Again, the slope is negative, so my K is the negative of the slope. And if I have the inverse of my reactant's concentration versus time and I get a straight line, then I have a second order reaction. And because the slope is positive here, the slope is equal to K. All right, so let's just take a quick look at this. What is the order of the reaction for A2 to 2A? This is typically how this gets asked. Because it's the plot of the inverse, this is going to be second order. So what is the rate law? The rate law is rate is K times A2 squared. And what would the units be? This is a good question. So K is going to be rate over my concentration, which is always molarity squared. But listen, so this is what we have. It's moles. Rate is always going to be molarity per second. And I put that over molarity squared. So this is going to cancel out, right? And I end up with 1 over seconds over molar. So this is seconds to the minus 1, molar to the minus 1. Okay. You could also write this as second to the minus 1. And because molarity is equal to moles over liters, the inverse of molar becomes liters over moles. So whatever works for you. Okay, here's a question. Which plot represents a 0th order? It's this one, right? First order, it's the natural log, that one. And second order is the inverse, okay? Rate law for plot 4. So rate is equal to K times the concentration of A. That's the rate law. And identify the rate constant. It's the negative of the slope. Okay. Compare the rate of disappearance of A in plot 1 versus plot 2. Okay, so the rate of disappearance is constant here in plot 1. Whoops. Okay, see, no change in the rate. Can't quite look at this plot and know, based on how it's plotted, that this what's happening to the rate of disappearance, but you know it's second order. And what that means is, as I change the concentration of this, I square this, so the rate is much faster disappearance. Okay, so I am squaring the change in my concentration, right? So it's going to have a much greater impact on my rate. All right, we're going to skip over that one. All right, potential energy diagrams are really important. You get a lot of these, and you got to be able to read them. Okay, so when I start over here, this is always my reactance. This is my product. Reactance. This is my product. So if I look at the forward reaction, the time, the distance from where that starts to the peak is my activation energy, energy of activation. Okay. If I were looking at the reaction going the opposite way, here these become my reactants. So the activation energy changes. So the activation energy is now going to be much higher for the reverse reaction. Okay. All I have to do is draw that. Now, one of the things that does not change is my enthalpy. My enthalpy is always reactants versus products. So this is my enthalpy, right? And because I start as a higher energy and end up with a lower energy, this is exothermic, right? I'm losing energy. All right. My reverse reaction is going to have the same magnitude of the enthalpy, but the opposite sign. That will be endothermic, right? Same magnitude. Same thing over here. Reactants, products, activation energy is from where I start my reactants, where the potential energy is, to the top of that mountain. The enthalpy change is going to be this enthalpy change. Going from reactants to products forward direction, it's going to be a positive. Okay. Going in the reverse direction, it's going to be negative. It's going to be exothermic, so I end up at a lower energy. Okay. So one of the terms is activated complex. Activated complex is the stuff at the top of the hill. It's kind of the mess of stuff. It's kind of the particles rearranging before I start to get products out. Okay. Okay, so you get asked this question a lot, and there's a verbatim answer you got to give. Based on what we learned, why does the reaction rate increase with temperature? Because if I increase the temperature, I have a larger portion of molecules with sufficient energy to overcome the activation energy. Okay. Actually, I think we're going to stop there, and then I'll talk about mechanisms on the next podcast.